The paper I'm going to be presenting today is Efficient Algorithms and Lower Bounds for Robust Linear Regression. Linear regression is a well understood and common problem in the statistical field with many different variants and angles of observation. This paper aims to study linear regression in the form of a robust model where some epsilon fraction of the given samples are adversarially corrupted. However, in order to do this, the trade-off between sample complexity, computational complexity, and robustness must be considered so that these optimal and efficient algorithms that are created still keep this in mind. Estimation will be a key and important feature in this problem, specifically among robust algorithms. Previous estimators that maximized efficiency could only handle an insignificant amount of outliers in these high dimensional settings. However, recent work has seen efficient, robust estimators for basic high dimensional statistical tasks, which leads to our formal setup. In the realizable setting, linear regression can be explained by this equation: y sub I equals beta times x sub I plus n sub I, where x sub I comma y sub I are from a multi-set of labeled samples, with x sub I being in the set of d-dimensional real numbers and y sub I being in the set of real numbers. It is then assumed that there exists some unknown distribution d, such that x sub I is in d, and an unknown vector beta, such in the d-dimensional set of real numbers, and we can treat n sub I as some kind of noise. Then the ultimate goal is to compute a hypothesis vector b hat such that the L2 norm of the difference between beta and beta hat is small. First, we will take a look at the robust learning algorithms presented by the paper. In the case where the covariance matrix is known, the paper achieves a robust learning algorithm with a near optimal sample complexity running in polynomial time. This leads to theorem 1.2, which relies on the main observation that robust linear regression can fundamentally be simplified or reduced to robust mean estimation. This theorem 1.2 is considered the basic algorithm, and one pitfall to this algorithm is that the error guarantee is dependent on the magnitude or L2 norm of beta, and it does not approach zero as sigma approaches zero. Therefore, we would like to eliminate the occurrence of beta, and in order to do this, theorem 1.3 is required, which achieves the minimax optimal error, a logarithmic factor of 1 over epsilon. The second part of this paper's results are regarding the statistical query lower bounds that establish a trade-off between sample complexity and computational complexity for robust linear regression, and this is in the case where the covariance is unknown. The statistical query, or SQ algorithm, provides an estimate of the expectation of the function of a function on a random sample from the input distribution, given any bounded function on a single domain element. And the paper's main negative result is proving that this SQ lower bound gives evidence that if X has an unknown covariance, it is computationally hard to approximate B, given significantly fewer than D squared samples. And the reason that this result is interesting is because this learning problem can be solved with D samples to optimal accuracy. Now we will move on to the actual algorithms posited by the paper, looking at both the basic and the main algorithm. The basic algorithm achieves the performance guarantee that we saw in theorem 1.2, and the algorithm either returns an estimate of beta or a set of data points that will be passed into another iteration of the algorithm. The basic algorithm relies on the fact that Yx is an unbiased estimator of beta, but in the presence of adversarial corruptions, the problem morphs into being able to robustly estimate the mean of the distribution of Yx. The key observation that enables the filtering framework to apply is that an epsilon fraction of corruptions cannot corrupt the mean of a distribution by a lot without affecting its covariance. This leads to the main algorithm, which establishes theorem 1.3's performance guarantee and improves on the basic algorithm by removing the log beta dependence. This approach gives an error of O of epsilon of the square root of beta squared plus sigma squared. And now the full proof of the lower bound of result of the paper. This main proof relies on a given distribution of x, y times q, and a sample set that we observe from Q prime. Here, Q prime can be assumed to be a mixture of Q and some noise. Then, given a statistical query Q prime, the claim is that beta cannot be approximated well without needing impossibly strong precision if the covariance is unknown. Concretely, what this means, following off 3.1, we can say that beta cannot be estimated to within O of square root epsilon with fewer than exponential and D queries. The consequence of this is that given an x conditioned on y for any non-zero beta, x will have some non-zero mean in the beta direction. It can then be shown that we cannot find the direction of beta with an SQ algorithm. So to recap, the main contributions of this paper were positive results and one negative result. The positive results arise from the case where covariance is known, and where the robust learning algorithm for linear regression that has near optimal sample complexity runs in polynomial time, and it also achieves an error guarantee that scales with the L2 norm of the target regression vector. And the main negative result is in the case of unknown variance, where the use of SQ lower bound shows that a trade-off in sample size is inherent. It was proved using a statistical query lower bound, again giving evidence that if X has unknown covariance, it is computationally hard to approximate beta well, given significantly fewer than D squared samples.